You know, there are certain facts about the world that we just accept. They're kind of like the furniture in our mental living room.
Right.
We learn them when we're kids, they seem to make sense, we pass the test, and then we never really question them again.
It gives us a sense of stability. We like to think we understand the basic mechanics of reality.
Exactly. And one of the biggest, most comfortable pieces of that furniture is our understanding of heat. If I stopped someone on the street and asked, why do things expand when they get hot? What's the answer I'm going to get?
Oh, you're going to get the standard textbook answer. They'll say that heat is energy, and specifically it's kinetic
Where's
energy.
that jiggle theory?
Precisely. You add heat, the atoms get excited, they start vibrating faster and faster,
Yeah.
and because they're moving so much, bumping into their neighbors, they push each other away. They need more space,
Yeah.
hence thermal expansion.
It's the mosh pit theory of physics. The music gets louder, that's the heat, the people dance harder, and the circle opens up. It's so intuitive. It's on Wikipedia. It's what I learned in school.
It is remarkably intuitive.
But, and this is why we're here today, what if that comfortable piece of furniture is actually wobbly? Or maybe it's not even a chair at all.
I would say we're about to upset a lot of high school physics teachers.
We are doing a deep dive today into a paper by Jerry Z. Liu titled, Is Thermal Expansion Due to Particle Vibration? And spoiler alert, the answer he proposes is a pretty resounding no.
It really is a disruption. And
Yeah.
we aren't talking about a minor correction here. This isn't, moving a decimal point. We are talking about finding a massive hole in how we calculate energy in things like gasoline and realizing that our definition of temperature itself might be fundamentally flawed.
So we're going to get into some really wild territory today. Invisible springs, why water breaks all the rules of physics, and why your car engine might be misunderstood. But let's start at the beginning, the vibration theory. Why does Liu say this standard jiggle explanation is wrong?
So the idea of hot things wiggle isn't completely wrong. Atoms do move, we know that. But using that wiggle to explain why a solid object physically gets bigger, that's where the logic starts to break down. Liu uses this really great analogy in the source material to show why. He calls it the forest analogy.
I loved this visual. Walk us through it.
Okay, imagine a really dense forest. The trees are your molecules. In a solid like a bar of steel, the molecules are more or less rooted in place, just like those trees. Now imagine a storm comes through, the wind. That's the heat.
Okay, I'm picturing it. The wind blows and the trees start swaying. They're vibrating.
They are. The branches are moving, the trunks are bending back and forth. But here's the crucial question. Does the forest itself get wider? If you measured the perimeter of the forest before the storm and during the storm, has the forest actually expanded?
No, not really. The roots are still in the ground. The edges of the forest are, pretty much where they were before.
Exactly. The movement is local. A tree swaying in place doesn't push the boundary of the forest out by 10 feet. And Liu argues that vibration in a solid is just like that. It's oscillation around a fixed point. It doesn't really explain how a steel beam gets significantly longer just from being hot.
That's a really good point. If I'm in a crowded room and I just start dancing in place, I might elbow the person next to me, but I'm not expanding the square footage of the room. I'm just occupying my own little space more aggressively.
Right. And to contrast this, Liu points to a railway track. This is the classic real-world example. On a hot day, a long rail track expands. And it doesn't just wiggle at the ends. The expansion is cumulative.
Cumulative, that's the key word there.
It is. Every single inch of that steel stretches a tiny, tiny bit, and all those tiny bits add up to a huge change over miles of track. If expansion were just atoms wiggling in place, like the trees, you wouldn't see that kind of uniform structural lengthening. The fact that the track gets longer implies the structure itself is stretching, not just shaking.
Okay, so the visual analogy suggests a hole in the theory. Trees don't walk. But physics usually needs more than metaphors. Is there any hard evidence that vibration isn't the cause?
The math is where the vibration theory really starts to fall apart. It leads us to what's called the monotonic problem.
Monotonic. Okay, break that down for us.
A monotonic function in math is one that only goes in one direction.
Yeah.
It always goes up or it always goes down. It never reverses. So if the theory is heat equals speed equals volume, then the relationship should always be consistent. More heat, more speed, more volume. Always.
But it doesn't always do that.
Not always. And the big exception is something we interact with every single day. Water.
Of course. The weirdness of water. I feel like water is always the exception in physics class.
It's nature's little rebels.
Okay.
Specifically, if you look at water between 0 degrees Celsius, so freezing, and 4 degrees Celsius.
Right, so really cold water, just melted ice.
As you heat water up from freezing to 4 degrees, it shrinks.
It gets smaller.
It contracts. Now, just stop and think about the vibration theory for a second. If heat is just vibration, just atoms moving faster, how can you possibly explain that? You can't vibrate something into being smaller. If I run faster and wave my arms, I take up more space, not less.
That's true. I've never seen a mosh pit get tighter when the music speeds up.
Exactly. The fact that thermal contraction even exists is a smoking gun. It tells us there is some other mechanism happening that has nothing to do with atoms just bumping into each other. If the kinetic theory were the whole story, water should expand the instant it melts.
So we have the forest analogy, and we have water proving that heat doesn't always equal expansion. So if it's not vibration, then what is it? We have to follow the energy.
And this is the part of the paper that I found absolutely shocking. We need to talk about specific heat.
Specific heat. Okay, this is bringing back some high school chemistry memories. For anyone who hasn't thought about this in 20 years, give us the simple definition.
Think of specific heat as a kind of cover charge for a club.
A cover charge. I like that.
It's the amount of energy you have to put into a substance to raise its temperature by 1 degree.
Okay, so some things have a cheap cover charge. They heat up fast, like aluminum foil. Other things are expensive. They take a ton of energy to get hot, like a big pot of water.
Correct. Now, standard science, the kinetic theory, has a formula to predict what that cover charge should be. It says, okay, temperature is just average kinetic energy. So if we know the mass of the atoms, we can calculate exactly how much energy we need to speed them up.
It's a budget prediction. I think the cover charge is going to be $10.
Exactly. And does the prediction work? Well, it works beautifully if you're a noble gas.
A noble gas, like helium or argon.
Helium, argon, neon, monatomic gases, just single atoms floating around. For those, the prediction is like 99% accurate. The theory is perfect.
Okay, so the theory works for the really simple stuff. Why are we throwing it out?
Because most of the universe isn't made of helium. As soon as you look at complex molecules, polyatomic gases, liquids, solids, the theory just crashes and burns.
Give us the numbers. The paper talks about octane, right? Gasoline. That seems important.
Right. Octane is a long, complex molecule. If you use the standard kinetic theory to predict its specific heat, the theory gives you a number. But when you go into a lab and actually measure it, the real value is vastly higher.
How much higher? Are we talking like a 20% error?
We are talking about a 93% error.
93%.
The theory accounts for only about 7% of the actual energy needed to heat up octane.
That's just wild. That's not a rounding error. That's a we have no idea what is happening error.
Imagine your bank account was off by 93%. You think you have $100, but the bank says, actually, you have 7. You wouldn't say, oh, close enough. You'd say there's a massive hole where the money, or in this case, the energy, is just disappearing.
So let's just sit with that. We're pumping heat into gasoline. Only 7% of that heat is making the atoms move faster, the kinetic part. Where is the other 93% going? It can't just vanish.
It doesn't vanish. It hides. This is what Jerry Liu investigated. He wasn't satisfied with the, oh, it's just complex excuse. He looked at a whole range of substances and plotted that missing energy against their molecular properties. He was looking for a pattern, and he found a near-perfect one.
This is figure 1 in the source material. I remember seeing this graph. It's just a straight line.
It is. He found that the amount of missing energy correlates directly with the number of chemical bonds in the molecule. The trend line has an R-squared value of 0.98.
For those of us who aren't stats nerds, 0.98 is basically a bullseye. A perfect match.
It is irrefutable. The energy isn't disappearing. It's being stored in the bonds.
And this brings us to the core of this new theory, the invisible springs.
Right. We usually see molecular bonds drawn in textbooks as little rigid sticks connecting balls. But Liu says we need to stop thinking of them as sticks and start thinking of them as springs.
Okay, springs, like in a car suspension.
Exactly.
Yeah.
Or like a slinky holding two weights together. When you add heat energy, sure, the molecule might move a little faster, that's the 7%, but the vast majority of that energy is used to stretch those springs. The bonds pull apart against the forces holding them together.
So heat is actually, it's potential energy.
In complex substances, yes. It is primarily potential energy storage. You're stretching the internal structure of the material. That's why things expand. It's not because they're jiggling harder. It's because the springs are physically being pulled open to store that energy.
That is a complete paradigm shift. It means we've been defining temperature wrong for A century.
Pretty much.
Hmm.
Liu is very explicit about this. He argues that temperature does not equal average kinetic energy.
Which is a bold statement because I'm pretty sure that's exactly what was written on the whiteboard in my physics class.
It's a bold statement, but if you look at how we actually measure temperature, the evidence supports him. Think about an infrared thermometer, the ones everyone pointed at our foreheads a few years ago.
Good point, click, beep.
What is that device actually measuring? It's not measuring how fast the atoms in your forehead are vibrating. It can't see that. It's not a radar gun for atoms.
It's measuring heat radiation, infrared light.
Exactly. It detects radiative energy. And radiation doesn't come from particles bumping into each other. That's kinetic. Radiation comes from electrons jumping between orbitals. That is a change in potential energy.
So the very tool we trust to tell us how hot something is telling us that temperature is about potential energy, not speed.
Right. The instrument we use contradicts the definition we use.
That is kind of unsettling. So if temperature equals kinetic energy is wrong, what's the right formula? Lou proposes a new one, doesn't he?
Yes, he calls it dynamic energy.
Dynamic energy, what's the math?
The formula is simple. T equals R plus U plus K.
R, U, K. Break those down for us.
Temperature T is the sum of radiative energy, R, potential energy, U, and kinetic energy, K.
So it's a mix, not just one thing.
It's a mix. But crucially, in liquids and solids, the kinetic part, the movement, is just one slice of the pie, and often a very small slice. It's a side effect, not the main event.
I like the analogy you used when we were prepping the car engine.
Right. Think of a car speeding down the highway. The engine is doing the work, but the car also makes noise. The roar of the engine, the tires on the road.
And the noise is related to the speed, faster car, louder noise.
Exactly. There's a correlation. But the noise isn't driving the car. You wouldn't say that Ferrari is propelled by sound. The sound is a byproduct.
So in this new model, kinetic energy, the vibration is the noise.
Yes. The engine driving everything is the potential energy stored in the springs. The vibration is just the noise the molecules make while that's happening.
That clarifies it so much. But it does raise a question. If heat is primarily stored in these springs, why do things vibrate at all? Because we know atoms do move. Where does that motion come from if the energy is all locked up in a spring?
That's a fair question. This is where Liu introduces a mechanism he calls transimpact.
Transimpact. Sounds like a summer blockbuster.
It does, doesn't it? The mechanism is fascinating. It starts with an electron.
Okay, zoom in. We're at the atomic level now.
An electron absorbs energy, maybe from light, maybe from heat. When it does, it jumps to a higher orbital. It gets excited.
The quantum leap.
Yes. But here's the physical consequence that gets ignored. When an electron jumps to a higher orbit, the effective size of the atom suddenly expands. And this happens in nanoseconds.
So the atom gets fat instantly.
Instantly fat. Liu uses the analogy of popcorn. Imagine a kernel of corn sitting right next to another one. Suddenly, pop.
Yeah.
One of them bursts open. What happens to the neighbor?
It gets shoved away hard.
That is transimpact. The sudden expansion of the electron cloud creates an explosive repulsive force. That shove is what creates the kinetic movement.
I see. So the movement isn't the heat. The movement is caused by the atom expanding like popcorn because it stored the energy first.
Correct. The potential energy, the orbital jump, converts into kinetic energy, the shove.
And does it work the other way? Can motion turn back into heat?
Yes, and he calls that impact trans, the reverse process.
Impact trans.
It explains friction. When you rub your hands together, you're creating kinetic motion. Those collisions jostle the bonds and knock electrons around, which then release energy as radiation is heat.
So friction isn't just magic. It's kinetic energy slamming into atoms, changing their potential energy, which then radiates out as warmth.
It unifies the whole system. Potential, kinetic, radiative, they're all constantly swapping forms. That's why he calls it dynamic energy.
Okay, this new framework, we need to take this back to the mystery of water. The vibration theory couldn't explain why water shrinks when it warms up. Does the spring theory explain it?
It does. And it's actually really elegant. It comes down to a battle between the structure of the bonds and the stretching of the bonds.
Structure versus stretching.
Right. So in water, you have hydrogen bonds. At very low temperatures, like in ice, these bonds form a very specific rigid structure. It's like a scaffolding that holds the water molecules apart in a hollow pattern. That's why ice floats.
So cold water has this big open scaffolding.
Exactly. Now, when you add heat, two things happen at once. First, the bonds act like springs and they try to stretch, which would normally cause expansion. But secondly, that energy destabilizes the rigid scaffolding. the whole structure starts to fail.
The scaffolding
It
collapses.
collapses, and the molecules fall in closer to each other. This collapsing effect is much stronger than the tiny stretching of the individual bonds. So the net result is that the whole thing shrinks.
It's like a tent collapsing. Even if the canvas stretches a tiny bit, the whole thing takes up way less space once the poles are gone.
That is a perfect analogy. And this collapse continues until you hit 4 degrees Celsius.
And what happens at 4 degrees?
At 4 degrees, the scaffolding is mostly gone. The water is packed in. Now, if you keep adding heat, the collapsing is done. The only thing left to do is stretch the bonds. So the spring mechanism finally takes over, and water starts expanding like a normal substance.
That is such a satisfying explanation. The vibration theory just calls water an anomaly, but this bond theory actually explains the mechanics of it.
And it doesn't just explain the anomaly. It explains the magnitude of expansion in other things, too. If you look at Table 1 in the source, the correlation is just stark.
This is the water and gasoline comparison again.
Right. Let's look at the bond count. Water, H2O, has just 2 bonds.
Okay. 2 little springs.
Its expansion coefficient is relatively low, around 69. Now look at gasoline or octane. It's a monster molecule. It has 25 bonds.
Way more springs.
Way more springs. And its expansion coefficient is 317. It expands more than 4 times as much as water.
Because it has more places to store the energy.
Exactly. More bonds, more capacity to store potential energy by stretching. If expansion was just about vibration and mass, why would the number of bonds matter so much?
Right. If it was just about weight and speed, the numbers just wouldn't line up like this.
But if it's about springs, it makes perfect sense.
Yeah.
More springs equals more stretch equals more expansion.
It's really convincing when you lay it all out like that. It feels like we've been looking at the world with one eye closed. We saw the movement, but we completely missed the tension.
It really does force us to rethink internal energy. In liquids and solids, the kinetic part, the vibration, it's almost negligible. The energy is almost entirely stored in the bonds.
So let's bring this home. What's the big takeaway here? Why does this matter to someone who isn't a physicist? Why should you care if it's a spring or a jiggle?
The takeaway is that we need to stop thinking of heat as speed. Heat is storage. Thermal expansion isn't a crowd of people dancing. It's a network of springs being pulled tight.
And this isn't just semantics. This has real-world impact.
Oh, absolutely. It affects how we calculate efficiency in engines, how we understand phase transitions, even how we model the weather.
Like that 93% error in octane we talked about.
Exactly. That error exists because we were looking for motion where there was only tension. If you're designing an engine and you think all that heat is turning into pressure via motion, but 93% of it is actually just stretching the fuel molecules, your calculations are going to be wrong.
It makes you wonder what other things we learned in school are just convenient approximations that fall apart when you look too closely.
Science is just a process of being less wrong over time. The vibration theory was a good guess for simple gases. It was intuitive. But it failed to scale. Liu's dynamic energy theory seems to capture the complexity of the real world.
The hidden springs of heat. I will never look at a thermometer the same way again. I'm just going to be imagining billions of tiny springs stretching out
And popping like popcorn?
and popping like popcorn.
Next time you see water boiling or ice melting, you aren't just seeing movement. You're seeing a massive restructuring of potential energy.
That is a powerful thought to leave you with. But here's one final thing I want you to think about, something the source material hints at.
The what now question.
Right. If temperature is actually defined by this dynamic energy formula, radiation and potential energy and kinetic motion is just a side effect, do we need to rewrite the laws of thermodynamics?
That is the big question.
The laws talk about heat and work. But if heat is actually this complex mix, are our equations for things like entropy and efficiency fundamentally slightly off? And what other settled science is relying on an assumption as shaky as the swaying forest?
It certainly opens the door for a lot of new research. It's an exciting time to look at the basics again.
It sure is. Thanks for joining us on this deep dive into the hidden mechanics of our universe.
My pleasure.
We'll catch you on the next one. Stay curious.